In our last lecture, we looked at how astronomers learned about the various properties of stars. They developed methods to understand the distances to stars, their luminosity, their temperature, their composition, and even their mass. So this has actually transformed stars for us from tiny points of light in the sky to actual huge objects out in space, many light years away, that we can study and understand. Well, in this lecture we want to go to the next level. We want to take that next step, and what we want to do now is see what we can learn about the stars over their life cycle. In other words, how are they born? How do they live? And how do they die? To do that, astronomers developed a very powerful tool that we're going to see that enables us to trace the lives of the stars. This tool is called the Hertzsprung-Russell diagram, after the two astronomers who developed this early in the 20th century. Now, the Hertzsprung-Russell diagram is essentially a plot of a star's luminosity against its surface temperature. And as we take a look at our first example of one, you'll notice the luminosity increases on the vertical scale to your left. But notice importantly that it doesn't increase in a linear fashion, 1, 2, 3, and 4. No, it goes up by orders of magnitude. In other words, it's 10, 100, 1,000, 10,000. And the unit we're going to use here is solar luminosities. We had mentioned before that we don't really use watts or anything like that. We're going to use the sun as one unit of luminosity. Along the bottom horizontal scale, we see surface temperature. Now, normally we'll often plot things that increase to the right, but in this case we're going to do the opposite. Astronomers will plot the surface temperature of the star increasing to the left. So this is a very powerful tool, as I mentioned, that we're going to explore in this lecture and enable us to again understand the stars. Well, if we were to go out and take a random sample of many stars and plot their luminosity and their surface temperature, we would notice something very dramatic right away. And that is that by far the majority of them, perhaps 80 to 90% of them, fall along a line from the upper left to the lower right. This line is called the main sequence of stars. Notice that again, as the temperature increases, the luminosity increases. And we'll see the reason for this in just a few minutes. But for now, that's our first important point, is that most stars would lie along this main sequence, and there's a very important reason for that. Now, there are a few stars, again maybe 10 to 20%, that are not on the line. Some of those would be to the upper right in our diagram, and these are giant and supergiant stars. How do we know that? Well, very simply, they have a lower temperature but a higher luminosity. So clearly these are very large stars, as we'll discuss in just a minute. There are also a fair number of white dwarf stars found in the lower left of our diagram. And here we have the exact opposite. We have a higher temperature but a lower luminosity. So these are already subtle clues of what happens to the stars throughout their lifetimes, as we'll see as we go along. Now, before we go too much further, I want to focus again on that horizontal scale just for one more moment. And as you look closely, you'll see some letters there. These indicate categories that astronomers have placed stars into. We call this their spectral type. And you'll notice as you look closely that if you move from left to right, from higher temperature to lower temperature, the letters don't seem to make a lot of sense. They go O, B, A, F, G, K, and M. Originally, astronomers began to categorize them A, B, C, and D, but soon found that it made much more sense for us to put them in this order. Besides their particular spectral type, designated by the letter, stars also have a luminosity class. We mentioned those just briefly already. There's supergiants, there's normal giants, there's main sequence stars, and there's dwarfs. So, initially, we again see how we can simply plot these two properties of stars, begin to see the different types of stars. But let's summarize then what we can learn from our HR diagram. Clearly, we could always read off the temperature. Temperature, as you'll notice, is related to the color of the star and the spectral type. We also, of course, could easily read off the luminosity, and I hinted at we could also determine the size of the stars. So let's look at that just a bit closer, the size of the stars. You'll notice in our diagram that, again, the higher you are on the diagram, the more luminous the star is, and vice versa. The lower you are, the less the luminosity. We also made it clear that hotter stars are to the left, cooler stars to the right. So once again, a large star would have a high luminosity but a low temperature. And that would indicate a star with a great surface area from which it can emit light. Again, our giants and our supergiants. But let's go back now and talk a bit further about that main sequence of stars. Why is there this correlation, this relationship to high luminosity and high temperature? Well, here's one of our most important fundamental points of our lecture today. The reason we have the straight line is that main sequence stars are fusing hydrogen into helium in their cores to produce energy. And as a result, the more they fuse, the more energy they send out. And as a result, they would be, again, more luminous at a higher temperature. So if you'll notice in our diagram, we see exactly that. Main sequence stars that are very luminous are very hot, and they're over towards the left, the top left of our diagram. Whereas main sequence stars that are cooler are much down to the lower right of our diagram. We look a little more closely at our diagram and we begin to understand the various masses of the stars. You'll notice that here as well. Once again, we can use our sun as a unit, one solar mass. So clearly we could plot the sun at one solar luminosity and a surface temperature of approximately 6,000 degrees. That puts our sun roughly in the middle of the main sequence. More massive stars are to the upper left. They're hotter, they're bluer, and they're more luminous. Lower mass stars, on the other hand, are going to be cooler and again down and to the right. What's the range of masses that we see? Well, we mentioned briefly in our previous lecture that the very smallest stars that we truly can call stars are roughly 8% of the sun's mass, whereas those that are at the high end, so to speak, are about 150 times the mass of our sun. So quite a range there of stellar masses. Why is that? Why is it that a star that's more massive is going to give off more light? Well, fundamentally, it has to do with, again, the gravity. The higher the mass of the star, the greater the gravity is going to compress the center of that star. For that star to be stable, that core now must respond and at a higher temperature produce more energy to balance out that higher gravity. And so we do have a balance here between pressure and gravity. The higher core temperature is required to produce more energy to balance out the greater gravity of the high mass star. And as a result, if it's producing more energy, clearly it's going to give off more light. It's going to have a higher luminosity. So we begin to see again the relationships here between all of these various factors. Now, interestingly, the HR diagram can also give us an indication of how long a star may last on the main sequence. We'll see in future lectures that a star will not last forever on the main sequence. Eventually, it will use up the fuel in its core that keeps it on that main sequence. Let's take a little closer look at how that works. Let's picture, for example, a star with, let's say, 10 times the mass of our sun. It's a lot more fuel to burn, isn't it? But we already said that with more mass comes more gravity, comes a higher core temperature, comes a greater luminosity. And as a result, to produce that extra energy, that star must use up its fuel much faster. If it starts out with 10 times as much fuel, it's actually going to use it 10,000 times as fast as the sun. So as we'll see, the sun has a particular lifetime. We would realize then that a higher mass star would have a shorter lifetime than the sun on the main sequence. Now the opposite is true as well. Let's take a star with a much lower mass, perhaps only 10% of the sun's mass. Well, obviously it starts out with much less fuel to burn, but because it has lower mass, lower gravity, the core will not be as hot, and it will not burn that fuel as fast. And therefore, it will last much longer on the main sequence than our sun, only burning its fuel at approximately 1% the rate of the sun, and therefore it will live much longer than our sun. So we're going to see, again, tremendous differences in the lifetimes of stars depending on their mass. In fact, ultimately, astronomers consider mass the most important characteristic of a star. If we know the mass of a star, we can have a very good idea of how all the other characteristics will be. For example, again, its luminosity, its temperature, and its lifetime. So we're going to summarize that here. Again, the mass determines the fusion rate. The fusion rate determines the luminosity. That's essentially equivalent to temperature. And these are very sensitive to mass. In other words, a small change in mass means a great increase or decrease in luminosity and fusion rate. And that, of course, has a great effect on the lifetime. So we begin to get a sense now of the life cycle of a star. We'll get into more detail. But all of this information is now available and accessible to us on the HR diagram. So let's do a quick review on some of the properties we mentioned. Luminosity, again, can change dramatically. In our previous lecture, we saw it may be as little as 1/10,000th that of the sun, or as much as 1,000,000 solar luminosities. Surface temperature can vary from a relatively cool 3,000 degree surface to as high as 50,000 or even more on the surface. Mass, we said, can vary from approximately a low of 8% of the sun's mass up to approximately 150 times the sun's mass. And lifetime, on that main sequence, when the star is fusing hydrogen to helium, changes dramatically, anywhere from a mere 10 million years to more than 10 billion years, nearly the age of our universe. So we've already seen quite a difference in the stars depending on their mass. Here you see illustrated for you some artist illustrations of what different main sequence stars could look like. Notice that our higher mass star obviously is much larger because of its mass, but we said it must generate a higher core temperature and therefore a higher surface temperature and therefore a higher luminosity. That means it's going to have a much shorter lifetime. It would appear blue to you and I because of that high temperature. We move down just a little bit to another star, not quite as massive, not quite as hot, not quite of a short lifetime. And then we move down further to our sun, and we are very familiar with our sun. Ultimately, we go down to the very lowest mass stars. Again, very low gravity, very low temperature, very low luminosity, very long life. So a great variety of stars on the main sequence. Well, let's go back now and talk briefly about those other stars, those giants, and those supergiants. These stars, for various reasons, can swell to enormous sizes, as we're going to see in future lectures. Some are far larger than our sun. Giant stars could perhaps fill the orbit of Mercury. In fact, if we were to take a supergiant star, some of those are so large, if they were placed in our solar system, they would extend beyond the orbit of Mars. Earth would actually be orbiting inside the star. That's how huge a supergiant star may be. So what a dramatic difference in sizes of giants and supergiants. So one more time, as we again look at our diagram, we again realize that the higher the mass, the higher the temperature, the shorter the lifetime, and vice versa on the main sequence. But note now, our giants and supergiants don't necessarily follow that rule, do they? They're in the upper right-hand part of our diagram. And since they are simply larger. They have a high luminosity, but a lower temperature. So they're a little bit different than our main sequence stars in that regard, aren't they? Well, we're going to see in more detail in future lectures, but for now I'll just say that these giants and supergiants come from main sequence stars. We mentioned that at some point Main sequence stars are going to use up the fuel in their core, and they're going to go through some very dramatic changes. They're going to leave the main sequence. Now, they're not moving anywhere in space, but they're moving on our diagram. Their luminosity and temperature will change in such a way that they will move on our diagram to become giants or supergiants. And eventually, many of those giant stars will become our white dwarf stars, as we'll see in a future lecture. So we have lots to look forward to tracing more of the details of that story. This then again is how astronomers are able to learn about the life cycles of the stars. We'll see main sequence stars form. They fuse hydrogen and helium in their core. We would plot them on that main sequence for quite a long time, but eventually they will become cooler and more luminous and larger as they leave that main sequence and move up into the giant region and even the supergiant region. At some point I mentioned those giant stars will also change into white dwarfs. Clearly they'll have to lose a lot of their mass, but the point being that we have a great change among stars when they leave the main sequence. Well, I'd like to spend the last part of our lecture discussing star clusters. And the reason I want to do that is because it's an excellent way for us to see the power and utility of the HR diagram. So let me introduce just briefly then the two main types of star clusters. We have what we call open star clusters. Now here you may have as few as a few dozen, perhaps a few hundred, maybe even a few thousand stars. And these form together, as we'll see in our next lecture. These clusters are within our Milky Way galaxy. So as we look out, they may be some hundreds or possibly thousands of light years away. And we'll see what we can learn from them in just a moment. On the other hand, a very different type of star cluster is something we call a globular star cluster. These are composed of tens of thousands, hundreds of thousands of stars. Gravity has shaped them into more of a spherical shape. Now these objects reside outside our Milky Way galaxy, orbiting around it, as we'll see in a future lecture. One of the biggest differences between the two types of clusters is their ages. We're going to see that the open star clusters are not nearly as old as the globular star clusters. How do we know that? Well, here's where the HR diagram comes into play for us. Again, we're going to get into some more detail, but let's start with this fact. We mentioned that a star of higher mass will use up its internal fuel more quickly, and it will not stay as long on the main sequence, but rather it will move off to become either a giant or a supergiant. Then progressively less massive stars will use up their fuel and move off as well. So in a sense, if we were able to be around for many millions of years and watch various stars, the highest mass stars on the main sequence would be the first ones to move off. Then the next lower mass, and the next lower mass, and the next lower mass. And when you think about the fact that the highest mass stars tend to be more of that hotter temperature, that bluer color, we would say, well, the bluer stars are going to leave first, then the next lower temperature would be more of a whitish star, then more of a yellow, and finally more of an orange-red star. So how can we use this to get an idea of the age of star clusters? Well, what if we were to do this? What if we were to plot an HR diagram just for a star cluster, rather than all the random stars we might see in the sky? If we just look at the cluster's stars and plot them out, we'll see our main sequence if the cluster is young. But as the cluster begins to age, I think you see where I'm going here. The highest mass stars will change first, and they will move off the main sequence. And as a result, our main sequence will begin to get shorter. Some of those stars, again, moving off to become giants and supergiants. Well, the longer time goes by, more and more stars will gradually move off. Now, granted, this takes millions of years, and we can't sit around and watch one star cluster, but we can look out into space and see star clusters of different ages, all at various stages of development. Very much like if we had a random sample of humans, we might not be able to watch one human age in a day through their life cycle, But we could certainly notice younger children, adolescents, young adults, older adults, and senior citizens, and we could piece together the life cycle of humans, couldn't we? So we actually have a term for the place where that main sequence begins to end. In other words, where the stars begin to turn off the main sequence and move off to become giants and supergiants. And that's exactly what we do call it, the turn-off point. So if we were to plot the HR diagram of a star cluster and look to see how far, again, that main sequence extends, we could get a pretty good idea of how old the star cluster is. Astronomers can go into much more detail here. They can perform calculations, they can model stars, and tell us how long a star of a certain mass will live. But for you and I, we can certainly look at relative ages of stars. We may even choose to take the HR diagrams of several clusters and put them all on the same plot. Well, in that case, we would clearly see a younger cluster means that the main sequence would be much longer. The next older cluster would be not so long, and the next older cluster, and the next older cluster. So if we found a cluster with a very short main sequence, we would know it would be a very old star cluster. So astronomers are able to do that. They're able to look at a particular star cluster, plot the stars on the diagram, and get a very good idea of its age. Some are very young, maybe only a few millions of years old, and none of the stars have moved off that main sequence yet. So we know that it's a very full main sequence, a very young cluster. Others could be partway through their lives, perhaps tens or hundreds of millions of years. What are the very oldest clusters we've found so far? Well, globular star clusters are the oldest. In fact, the very oldest ones we found have very short main sequences. Most of their stars have moved off and become giants or supergiants. All that's remaining is the very lowest mass main sequence stars. So I think you can begin to see what a powerful tool the HR diagram is for us. Let's go ahead and do our summary of what we've discussed in this lecture. We saw that an HR diagram plots luminosity versus temperature, and that is surface temperature. That temperature, of course, related to its spectral type. We found that most stars fall on the main sequence on the diagram. Why is that? Because here is where the stars are generating energy by fusing hydrogen into helium in their core. We saw that the highest mass stars are to the upper left on the main sequence. They have a high luminosity because they have a high temperature, don't they? And they're pouring out enormous amounts of energy. But we also saw that the price for that was a much shorter time period, much shorter lifetime, so to speak, on the main sequence. On the other hand, the lowest mass stars, they're down in the lower right part of the main sequence. Here they have a very much lower internal temperature and a very much lower surface temperature. And as a result, they're using their fuel much more slowly, and they're going to live a long time on the main sequence. We began to discuss where giants and supergiants come from. We said that sooner or later, stars are going to use up their fuel in their core, and they're going to change dramatically. They're going to leave that main sequence. They're going to move to the upper right to again become either giants or supergiants. And we said that many giant stars are going to eventually be the ones to turn into our white dwarfs. Some of the very highest mass stars, by the way, are going to turn into neutron stars, a very special type of star that we'll be discussing in a future lecture. Finally, we saw a really good example of how to use the HR diagram to tell us about the ages of star clusters. If we plot the diagram just for the star clusters members and watch to see how long that HR diagram's main sequence is, we can get a very good idea of the age of the star cluster. So again, I think you can see how powerful this tool can be. Astronomers who study the stars use it all the time in many different ways, as we'll be doing in our future lectures. So I look forward to exploring, again, the life cycles of the stars with you in our next lecture.